Right, so let's give this a go. Question 1A, June 2013, paper 4. So we've got a triglyceride, and it's a triester. That's because we have 3 ester bonds. We've got 1 ester bond here, and 1 here. This triglyceride is hydrolysized with hot aqueous sodium hydroxide. So that's going to break the bond here, here, and here. And this structure in the middle is what's going to form the alcohol. So it's a triol. It's got 3 alcohol groups. 3 carbons means that it is propane 1, 2, 3 triol. You'll get the mark with or without the E, but if the next letter is a consonant, you should include the E on the propane. So next, we need to draw the structures of the other products that we produce. So one of our products is from the hydrolysis of this group here. My first step is to copy that out, that group out exactly as it appears. Already sensing I'm going to run out of space on this. Okay, now where I've got the bond break here, we are going to end up with an oxygen and a sodium. It's not a carboxylic acid because it was hot aqueous sodium hydroxide, not hot acid that we use for the hydrolysis. For the other part, this is going to be what forms the other product, and you can see that this piece and this piece are exactly the same. So once again, just switch to the pen. Once again, copying it out as it appears up here. It's quite hard to write with this pen. And instead of an acid again, we have the salt. Haven't quite left me enough space, but hopefully it's enough for you to see the answer. You get 1 mark for each correct structure, and then the 3rd mark for showing that it's a salt and not an acid. Okay, part 3 suggests why people who consume large quantity of this type of goat's milk may be more at risk of suffering coronary heart disease. This is a slightly tricky one, but part of this topic is about the fact that trans fatty acids, are bad for you. So if I go all the way back up to here, you'll be able to see that this group here is a trans fatty acid. Our functional groups are on opposite sides of the carbon-carbon bond. So that's a key word, that it's trans fatty acids. So it contains trans fatty acids. Which leads to or may cause high levels of LDL, or bad cholesterol. I'm afraid you have to spell cholesterol correctly to get the mark for the quality of written answer. So notice here, you have the pen. Really it's, in this case, for spelling. Right, next page. Okay, so first question's asking us why for aminophenol can behave as a base. You have to remember that bases are proton acceptors. So our nitrogen up here has a lone pair. It's rather hard for me to draw it properly, so you'll just have to accept it. That lone pair can accept a proton. Now you need to make it clear that it's a lone pair on the nitrogen. You can't just say lone pair. So the nitrogen is necessary, and you need to make it clear that it's a proton or H plus or hydrogen ion, but it can't just be hydrogen. Okay, moving on. Right, so it's produced by reducing nitrophenol, and it's asking you to do the equation. So if you're struggling a little bit with this, start off by, you don't need to do molecular formula for these. In fact, pretty much all the time you can do structural. You know that you're starting with nitrophenol, and you know what you're ending up with. Okay, you just have to work out how many hydrogens will need to be added in order to do that. Okay, so we've got an additional 2 hydrogen from here, 2 hydrogen here, but we're also losing 2 oxygen, and oxygen and hydrogen together make water. So we're losing 2 oxygen, that will make us 2 waters. Therefore we have 1, 2, 3, 4, 5, 6 hydrogen to balance it out. Okay, so we've got to do mechanism on this one here. They've given us the electrophile. So that's plus NO2 is our electrophile. Remember, the arrow has got to come from the electrons, and the electrons are in the curly ring here. Right, so 1 mark for a double-headed arrow from the ring to the electrophile. That gives us this intermediate. So you have to excuse my wonky writing. Now, the ring has broken at the top here, so that's where the plus sign is. This half circle must cover at least half of the ring. Okay, so next is our bromine bond breaking. So we have an arrow going from the bromine to the plus sign, giving us NO2. And possibly this bit's going to throw people. It's going to be Br plus. Okay, our bromine here lost an electron, so it's going to end up positively charged. And if we look, the overall charge as we go through each step is a single positive charge at each step. Overall it can't change. The charges need to add up. Lovely. Right, so on to part D. Identify the reagent in reaction 1. So each time you want to identify which part of the molecule is reacting, this is changing to this. So what have we added? If you look through, you will see that we must have added HCl or hydrochloric acid. Now the organic product of reaction 2, we're being asked to name this. So our basic molecule there is a phenol group, which is the benzene ring with the OH. And in fact, for aminophenol, we can just use that as our basis for naming it. So let's just try and give myself a little space to write it out. There we go. So we can use our 4 amino, and then we have 1, 2, 3, 4, 5, 6. We have 2 bromines, and they are on the 3 and the 5, and it's 2 bromines, so that makes it dibromo. Sorry, quite hard to write on this. Dibromo phenol. If you can't read my handwriting, refer to the mark scheme. Right, so the equation for reaction 2, you, as I said earlier, always don't go to molecular formula, always write out the structural for these. So this is what I'm starting with. Oh, sorry, draw it better than me, but I'm struggling a little bit with trying to draw in this little thing. And we're going to go to this here. Yep, this bit I am just copying off the question earlier up. And then we've got to work out what is being added and what's being taken away. We're adding in bromine, but we're losing the hydrogens that are here and here. That's where people are likely to slip up, because it's not just an addition, it's a substitution. We're substituting our bromine for a hydrogen. So we've got 2 bromines, each one swaps one of their, each bromine molecule swaps one of their atoms with a hydrogen, giving us 2 HBr on this side here. Okay, draw the structure of the organic compound formed from reaction 3. So we're reacting with sodium metal. It's the alcohol groups that will react with sodium. Won't react with sodium hydroxide, but sodium metal is reactive enough to react with an alcohol. So what happens is the hydrogen is lost and replaced with a sodium. You can include the charges if you want, but there's no need to, so I'm not going to. Right, on to dyes. This is azo dyes. This group here is the azo group, which kind of gives us what the use is going to be. Possible answers: dyes, pigments, food colourings. Okay, on the flowchart on the next page, we want the reagents and conditions for reaction 1, the structure for B, the reagents for 2, and conditions for 3. So there's quite a few bits. I'll go straight on to the next page. Right, so reaction 1. These ones are straight memory, I'm afraid. You need to learn your reaction mechanisms. To go from an amino to an azo dye, so this little group here, you're probably more likely to remember seeing it like this. Okay, so to get from there to there, it needs to be less than 10 degrees. You may remember faffing around with ice baths. And there's two answers you can give. You can either start off with nitrous acid, which is HNO2, or sodium nitrite and hydrochloric acid, which is how you make the nitrous acid. So nitrous acid isn't stable. We have to make it in the lab first of all. Okay, so either of those will give the answer. Now let's just move this up. We've made our diazonium ion, and reaction A and reaction compound A and compound B are going to combine to make compound C. Interesting. Okay. So what we're adding, so our molecule at the bottom is made up of this and this. We've already got this bottom part. We're trying to make this. So this bit is compound B. And the bottom part is compound A. To make compound B, we're going to be adding on that iodine. In order to do that, you need copper iodide. Even if you couldn't remember the agent, you should be able to deduce the structure for compound B. Okay, so the conditions for the final part of the reaction, we do need to keep it cold, admittedly, but that's not what it's looking for. It's looking for alkali. So state what is meant by condensation polymer. In order to get this mark, you do need to say it's monomers, more than two, so lots of monomers. If you put two monomers, you don't get the mark. They join together to make a polymer and another small molecule, such as water or HCl. On the next part, we're hydrolysizing. And so we've got to look at our structure of our protein up here and work out when we hydrolysize it what we make. So when we hydrolysize, our bonds are going to be breaking on each of the amine bonds here. So she found that fibrin contained the amino acid glycine and two others. So first of all, we have to eliminate glycine. So glycine is here. So glycine has two hydrogens coming off the central carbon. So here's a glycine and here's a glycine. And here's glycine. So we're not looking at those. We're looking at the other two ones that are present. And you can see that we have these two are the same. And let's pick another colour. And in the green we have a different one. So these are the two structures that we need to look at. Can I fit them both in? Yes. So we'll go for the blue one first. The amino acid, so first off I'm just going to copy the part that is unchanged. And when this is hydrolysized, the C double bond O becomes an acid and the NH becomes an amino group, as in amino acid. And on our other side, exactly the same. So our amino group, our NH becomes NH2. I'm running out of space, aren't I? Can I move this up slightly? There's our other amino acid. 1 mark for each one. Right. So our next one, we're looking at the isoelectric point. So the isoelectric point is a point where it's got zero charge overall. So it's a pH where we have 0 net charge, or the pH at which the Zwitter ion exists. So a Zwitter ion has a positive and negative charge, but 0 overall charge. And glycine, as we know, we have 2 hydrogens. So if it has 0 overall charge, the hydrogen from the amino group comes over to this group here, giving us a negative charge over here and a positive charge over here. So that's our Zwitter ion, without the arrow, obviously. Right. The process by which TLC separates amino acids is adsorption. So the amino acids adsorb to the stationary phase, and that's what separates them out. Although it's a little more complicated than that, stick to adsorption. So, chromatography, we've got a table of RF values and we want to try and work out what X is. You will need to get out a ruler to measure this, and to calculate RF you've got to measure this distance here and this distance here. Okay, and the RF is going to be, I'm just going to label them A and B. It's the distance moved by our sample divided by the distance moved by the solvent. And you should get somewhere between 0.53 to 0.62. Not quite sure what's happened there, which gives us methionine as our answer. Okay, on to the next. Draw the repeat unit of the polymer made from these 2 monomers. So it's going to be a polyamide, and what's going to happen is that these 2 parts are going to react, and then this part here is going to react with this part of a next molecule. So the repeating part I take off the H of our alcohol group, and we're going to lose water from this section here, So we lose the oxygen, go straight to the amine. I'm not doing the best drawing here, but hopefully it's enough for you to see. And then on this one we have the nitrogen. Ooh, I've made a slight mistake, haven't I? I'm going to lose that oxygen. That's going to bond straight on to the nitrogen here. There we go. That's our repeat unit. Byproduct's going to be water. You don't need brackets, but I'm just in the habit of it now. So this one is going in the opposite direction. We've got to work out the monomers that will make up this. So we have an ester group here, and then an ester group formed from these two. I'm going to start with this side. Now this has got to be the alcohol, oxygen, and on the other side also made from an alcohol. So the alcohol that would make that would be this, and on the other side, let's change colour, we've got a carboxylic acid group from here and a carboxylic acid group here. I've made a real mess of that, I appreciate. Ooh. Okay. Right, so polymer D reacts with the third monomer to form an addition polymer. We've got the repeat unit there. Wants to know what the structure of the third monomer is. So with an addition polymerization, the part that we're looking at, let's pick yet another colour as if it wasn't busy enough, is going to be this double bond here. Okay, I'm going to see if I can wipe everything off. No, I can't. Okay, so this double bond here is what we're looking at. If you compare this with this, you can see that the point that we're adding on is here, and here. So it's a nice tricky one, this one, isn't it? However, we know that we're going to be adding this on. Okay, and what happens with these is the double bond that was here breaks and attaches to the next one. So there will be a double bond here that broke and formed attachment to the next one. So this, not very well drawn. I'm blaming the tablet. I can't do very good lines on this. That's going to be our monomer. Nice fiddly way of asking a straightforward question. Okay, so now we're on to question 4. And it's a case of completing off our flow chart here. So reaction 1, we have sodium dichromate, which is an oxidizing agent, and what is it going to oxidize? It's going to oxidize here and here, and it's excess and it's reflux, so it's going to oxidize as much as possible. So I start off and I draw the bits of the molecule that are not affected, and then I think about the two that are affected. So this group here is a secondary alcohol, so that's going to form a ketone when it's fully oxidized, and this group here is a primary alcohol, so that is going to form a carboxylic acid when it's fully oxidized. Sorry about the wobbly lines. Right, now on the next one we are reducing this group here. Okay, and you guys only know one reducing agent, which is sodium boro tetrahydride, this one here. Right. So that's us completed the flowchart. On to the next question. So reaction 1 was with the sodium dichromate. It's asking you for the colour change when it's oxidised, and you should remember this by now. We've done it a lot of times. It's orange to green. Okay. Now I've already slightly touched on this. I mentioned that it was heated under reflux with excess. That's to ensure fully oxidised. But just saying fully oxidised won't be enough to get the mark. You need to say either that you ensure carboxylic acid formed, or conversely, you can say to ensure that aldehyde is not formed. Okay, or something to the effect of distillation would form the aldehyde. So the type of reaction in reaction 2, they'll allow reduction, but strictly speaking it is an addition reaction. We are adding hydrogen to it. So as I say, reduction will get you the mark. So chemical test, to test for a carbonyl group. They'll allow Brady's reagent, which is the easiest way to remember it, or 2,4-DNP. If you want, you could remember 2,4-dinitrophenylhydrazine, but I rather doubt you can be bothered with that. Positive test with this is orange precipitate. So it'll accept yellow or red. Okay, so E is a single stereoisomer. Draw the structure of one other stereoisomer of E and state the type of stereoisomerization. So there's no carbon-carbon double bonds, so it's not going to be EZ isomerization. That leaves us with optical isomerization. Just, I haven't got a picture of it on this page. So on the previous page, you're going to have to identify the chiral carbon. That's a carbon that's attached to 4 different groups. I'm not completely sure I've got this drawn the right way, just bear with me. So this is the one you've got on your sheet. Okay, we need to identify one of the chiral carbons. There's actually 2 that I can see. So we've got one here and one here. Both of these are chiral. In order to do the stereoisomer, you're going to need to flip one of these bonds that's coming forward. You need to flip it so it's going backwards. So that would give us is one correct answer. Okay, so what I've done is I flipped this bond, and instead of it coming forward, it's now going backwards, remembering there's a hydrogen on there that we can't see. There's more than one correct answer. Have a look at the mark scheme. This type of isomerization is optical. Okay, So we have 4.56 grams was converted into G using the method on the previous page. We form 3.5 grams of G and we need to calculate the percentage yield. We've got the molar mass of E just to make our lives slightly easier. So 4.5 grams of E, if we divide by the molar mass, will give us the number of moles of E. And if we had 100% yield, that would be the number of moles of G. So what we need to do is work out the number of moles of G we actually made. Okay, so this is our mass of G, and the molar mass is 174, which you will have to work out, giving us 0.181 moles. So this is what we would expect to make, because 1 mole of E makes 1 mole of G. But instead, this is what we've actually made. So to work out the percentage yield, we do our actual yield divided by our theoretical times 100, which would give you 63.5%. All answers must be 3 significant figures. Okay, on to the next one. So compound G is refluxed for several hours with a concentrated sulfuric acid catalyst. An ester and a small organic molecule are formed. So a slightly tricky one, but should be able to work it out. If we're forming an ester, we've only got 1 molecule to start with. So as we know, in order to form an ester, we need an alcohol and a carboxylic acid group. So it must be reacting with itself. This is one of their favourites, is to throw in a cyclic molecule or have a cyclic molecule breaking down. So our product, I'm going to draw it down here because I'm not sure I can fit in the box, is going to be the alcohol. We're going to be losing a water from here. So this is now going to connect directly to the alcohol. Double bond O left over like this. Oh, I'm not forgetting this part coming off. And our byproduct, we're making an ester, is water. Okay, so nice big space here for doing this calculation. And we have carbon, hydrogen and oxygen. And we're trying to work out or show that the molecular formula is C10H12O2. So I'm going to make a little table with this. We have 73.15 of this and 77.73%. It's a percentage, so it's going to add up to 100. So 100 minus 73.15 minus 7.37 will give you whatever's left over is your oxygen. So that's 19.48. So to work that out, I did 100 minus the percentage of carbon minus the percentage of hydrogen. Gives me the percentage of oxygen, which is 19.48%. 0.48. Do we get a mark for that? No, you don't get a mark for that. Okay, so this is percentage. Our next step is to work out the number of moles in 100 grams. So for each one, we need to divide by the molar mass, which will give us the mole ratio, or the number of moles, sorry, yeah, in 100 grams, 6.1, 7.37 and 1.22. To calculate the ratio, we divide all of them by the smallest one, which in this case is the oxygen. So each of these we're going to divide by 1.22. Giving us 5, 6 and 1. Now this is our ratio, which means our empirical formula is C5H6O, and the mass of the empirical formula, if you add these up, 5 carbons, 6 hydrogens and an oxygen, that's going to be what, 60 plus 6 plus 16 equals 66 equals 82. Okay, as we know that the MR of the whole thing is 164, that's the question. We must have, which is twice that of the empirical formula. The molecular formula must be C10H12O2. I'm not going to have space to write this, but I'm trying to write molecular formula in the bottom here. Just forgive the handwriting, I'm trying to cope with these pens. Okay, right, so we have the carbon-13 spectra here, and we've got to look at how many carbon environments we have. Carbon-13, remember, the height if the peaks don't mean anything, we've got no splitting patterns, so we literally are counting 1, 2, 3, 4, 5, 6, 7. Okay. So now we've got our compound and our NMR spectra, which we will be coming back to later. This is going to be a pain, not going to be able to look at this when I'm going through it. Right, so the next part is using our two spectras to deduce our compound. I'm going to start on the carbon-13. We know we have 7 different carbon environments and 10 carbons in total. But what can we work out from this? The important two to look at is we have a peak here. So a peak at 185, suggesting an ester group. Okay, and peaks, the peaks between 220 and 260, these ones here, sorry, 120 and 160, that suggests a benzene ring. The ones down here are carbon-carbon bonds, so you've got to use your data sheet to do these. I would just do a sentence for each peak and each and what you're deducing. Right, moving down and having a look at the hydrogen. Again, slightly more complicated. I'm going to label on the diagram. So we have a peak at 1.2 here, and this is a doublet at 1.2. So using our data sheet, that's going to be RCH. And the integration curve is, you can measure it between here and here. Relative to the others, that's going to be 6 hydrogen. Okay, now our next one, we've got a multuplet here. And the multuplet has actually got 1, 2, 3, 4, 5, 6, 7. So 7 peaks, therefore 6 neighbouring hydrogen. And the fact we are at 2.7 suggests that it is this group here. Okay, and our final one, in fact, you don't have to measure the integration curve, of course. It gives us a number of hydrogens. It's making it more complicated than it needs to be. We got a peak at 7.3. This is another multuplet. But being here, it suggests, with that shift of 7.3, it suggests the benzene ring. Okay, right, so we've got to use all of this information that we've just gathered in order to work out what our mystery substance is. What I suggest you do is with all of the bits we know, we can try and put them together and then work out if it adds up. So let's just try and summarise everything. Okay, I'm going to start myself off with this bit here. So we know that we contain this structure, and we know that this hydrogen here has 6 neighbouring hydrogen. Okay, so 6 neighbouring hydrogens. There can't be, it's unlikely to be any hydrogens attached to that one. Because we still need to find space for the benzene ring, but if we have 2 methyl groups here, that gives us 6 neighbouring hydrogens. So the section in blue, having said that, I'm not going to undo that. The black hydrogen, we've got 1 hydrogen that matches here. Now the blue ones, the ones I've drawn in blue, they've got 1 neighbouring hydrogen. So these guys here in blue, they've got 1 neighbouring hydrogen, which means, and there's 6 of them, so the peak that I've circled in blue refers to that. We've got 5 more hydrogens to account for. We know they're likely to be a benzene ring. And now that benzene ring, what I haven't popped on yet, we've got 1 more oxygen, So if it was an OH group attached to something, we would always find a singlet peak for the OH group. So the fact we don't means that it's got to be between the carbon and the benzene ring. And that gives us that. That's 1, 2, 3, 4, 5 hydrogens. Now it's all put together as one peak there, but what we actually have is we've got 5. We would have 1, 2, 3 peaks, but I think what's happened is they've all overlapped each other to form that one peak there. Should have picked another colour, shouldn't I? There we go. So what we've got is, although there are 3 different hydrogen environments, they've all overlapping each other to give us one kind of messy multuplet there. Okay, hopefully you guys got that one. That's the final question, isn't it? So well done for getting this far, and I'm going to save it. So why do we add TMS? TMS is the standard for chemical shift measurements, or we use it for calibration or reference. Any of those words will get you the mark. So we include an integration trace. The integration is the area under the curve, is perhaps how I've been talking about it. It gives you the relative number of hydrogens in each environment. I'm not going to write this out, I'm afraid, so have a look at the mark scheme if you want to see it written. Right, so now we need to determine structure L. Referring to the spectra, which is on the previous page, which is a bit of a pain. So let's pause for a second. Okay, right. So if we start by looking at the carbon-13 to begin with. No.